So in this video, we're going to look at another part of 2.6, the special functions. This one, we're going to look at piecewise functions. This one is a little more challenging because there's several things going on in each one of these problems. And there's two kinds of problems that you're going to see. And I'll try to break them down one at a time and give you a sense of what these should look like and what the equations should look like, what the graph should look like. So we'll kind of just go from there. Pause as you need to. Okay, they're called piecewise function because they literally look like they're broken up into pieces. So when we're used to looking at a linear function, for example, or an absolute value function, for example, those are continuous. They keep going. There's no holes in them, and they're kind of smooth, so to speak. But in the piecewise functions, they're literally going to be several different pieces of functions of graphs, and then we're going to write equations for them, we're going to graph them, and you'll kind of see how that looks like. So what we got to do is we have to analyze and treat each piece differently. Each piece has its own equation associated with it, and we're going to use those and write those. So this first example, and it'll look like this. What this tells us, since there are two different equations, that there are then two pieces. What's important here is we have this f of x equals x minus 2 if or when x is less than negative 1. If x is not less than negative 1, then we use a different rule. So the other rule is f of x equals x plus 3 if x is greater than or equal to negative 1. So these different pieces tell us to do different things for different x's. That's what the piecewise function is all about. Now, the best way to look at this is to think of it as y equals x minus 2 for when x is less than negative 1, as I just mentioned, and think of it as y equals x plus 3 for when x is greater than or equal to negative 1. So notice in this problem, we have conditions for less than negative 1 and greater than or equal to negative 1. So negative 1 is sort of our dividing line, so to speak, in this problem. So here's what we're talking about. This x equals negative 1 is our dividing line. So I've just drawn that on there. And if you want to know, this equation of this vertical line is x equals negative 1. So what this means is we're going to use one rule where it's less than negative 1 over here, a different rule when it's greater than or equal to negative 1. So on the next slide, I've kind of color-coded it all for you. So here's what we're talking about. This red line, y equals, or f of x equals x minus 2, is for when x is less than negative 1. That's this red region over here, because over here is less than negative 1 for x. The blue region is x plus 3 if x is greater than negative 1. So this is the blue region. So we're going to have a little bit of a graph in the red shaded region using the rule y equals x minus 2. Then we're going to have another part of the graph in the blue region. So this graph can't go to the blue region, and this graph can't go to the red region. You got to keep them separate. Now, you don't have to shade the colors like this, like I did. I want to show you this so you see what it looks like and how we operate with it differently. But, I mean, if you want to shade them that way, feel free. Go ahead. But you do not have to. So here's how we're going to start. We're going to just worry about this top one first, y equals x minus 2, okay? And what I recommend in these piecewise functions is to start with the boundaries as an input. So in this case, the boundary, that's what this is, the condition x less than negative 1. We're going to start with x equal negative 1. We're going to plug it in, and then we're going to see what that y value equals, okay? So, of course, you look at this, you know the y value equals negative 3. So what this means is I have a point at x equals negative 1, y equals negative 3. Here's where it gets a little tricky. X doesn't actually equal negative 1 for this rule. It's less than, not or equal to, just less than. So like we did when we did linear inequalities, we're going to have an open circle at the point negative 1, negative 3. And it's going to look like that. So here's the point, negative 1, negative 3. So I go over 1 to the left, down 3. It's an open circle because it's less than negative 1. It can't actually equal negative 1. right? Then from here, what we're going to do is use the slope to come up with more points to come up with our line. So the slope for this equation is 1, all right? And we're going to use that slope to come up with more points. Well, 1 is the same as 1 over 1. So what I would do is I would go up 1, right 1, but what happens? I go into the blue region, which is not where I need to be. I need to be in the red region. So what we're going to do is we're going to change this slope around. We're going to manipulate it a little bit so that we can get it counting this way. So what we can do is just change it both to negative. -1 over -1. That will mean I get to go down and left. And so I get a point over here, and then I can go down and left again and get a point over here, and down and left again and get a point over here. So I'm going to get a bunch of points like this that kind of look like that. So had I used the 1 over 1, my points would have ended up in the blue region, which that's this rule. That's not the top rule. So I changed it around because I realized I was going the wrong direction. So I just went and changed these both to negative, which negative over negative is still positive, still equals 1. Down 1, left 1, down 1, left 1, down 1, left 1. Then I connect those. There's that piece, okay? Notice it didn't keep going. I didn't make it go into the blue region. I just did a piece of that entire line, okay? Then we do the exact same thing with this rule in the blue region, okay? Here's how that's going to look. So now I'm at x plus 3. I start with my boundary again, but this time, because it's greater than or equal to, I can actually fill the point in. So I'm going to plug -1 again. Now, if this problem, they both happen to be -1. You're going to have other problems where this one might be -1 and this one might be 3. They don't have to be in the same point. It's okay if there's a big space in between the pieces. This is just one example. Anyway, I plug the -1 in for x again, and I get 2. So what this tells me is I have a point at -1, 2. So I just plot that. And since it's or equal to, I can fill it in. So that's where it is, -1, 2. And now I'm going to use my slope again. The slope is 1 again. And now, if I make it over 1, I go up 1, right 1. I'm in the blue region. That's good. I don't need to change the slope around like I did here. So I go up 1, right 1, up 1, right 1, do that a bunch of times, and I get a bunch of points. Then I connect the dots. I have my pieces. So this is what a piecewise function looks like. I got 2 separate pieces right here. 2 equations, 2 pieces. The last thing we need to do is come up with the domain and the range. And we talked about before the domain if there's walls, okay? This one shoots off to the right forever, so there's never going to be a right wall. This one shoots off to the left forever. There's never going to be a left wall. And there's no gap in between going this way. There's no gap. There's no horizontal gap, vertical gap between x's because these points, so if I was on this line, I'd be moving along. Oh, yep. Here, now it jumps straight up to this one, so the -1 is covered, and so there's no walls. So in this case, my domain is all real numbers. The range is a whole different story because we look for floors and ceilings. Now, this piece doesn't have a ceiling. It goes up forever, but it has a floor. This piece has a ceiling, but it doesn't have a floor because it goes down forever. So in this case, I have 2 separate things that I'm going to have to write for the range. And the fact is I have this giant gap in between where there are no y values associated with this function, with these graphs. There are no y values in this shaded region here. So that's how I know that I have a floor up here and a ceiling over here. So then I just actually write 2 inequalities because this one is greater than or equal to because the point is filled in, greater than or equal to 2. This one is less than -3. So we both of those. So this top one has a floor greater than or equal to 2. This bottom one has a ceiling less than -3. And again, it's less than because the point is open. It's or equal to because the point is closed. All right. So this is what you're going to have to do in part in piecewise functions. Now, The other thing could be true. You could be given a graph, and then you could be told, all right, go ahead and write the equations out and see what that looks like, all right? And that's what we're going to do next. So here's a piecewise function. We have 1, 2, 3 pieces, which means there's going to be 3 separate equations. So when we write a piecewise function and it tells us it's f of x, that's important too. The graph will tell you it's f of x. Sometimes it'll say g of x or h of x or something. Sometimes it'll even say y, and then you can write y. But make sure you follow along with that, okay? So here's how we started off. We started off by writing f of x. Again, you're thinking that this is y, and we put this big, long brace because we're going to have 1, 2, 3 equations. And notice over here what I've done. I've shown you, because since the if parts are always x, there are walls. I have a right wall for this piece, and it goes that way. For this piece, I have a left wall and a right wall. And for this piece, I only have a left wall. So what we're going to do first is write the if statements for each one. Okay, so let's focus on this top one here, all right? This value, this x value, lines up with 1. And I'll extend this line down for a second. Let's see if I can do this. I'll extend this line down so you can see that it hits at 1, x equals 1. So 1 is the smallest value it could be, but it's an open circle. So that tells me I'm going to have a less than or greater than. Since it's pointing to the left, that means it's 1 or less. So this part, the if part for this piece, is it'll say if x is less than 1. Okay, that's the first piece. Now let's look at the second piece. We have a left wall at 1 and a right wall at 2. And both points are filled in. So I'm going to have less than or equal to. And I like to put them in that order because then it's easier to do. Here's a 1, here's a 2. Basically what we're saying is x is in between 1 and 2 and included. So what we say is 1 is less than or equal to x, which is less than or equal to 2. And that looks like this. And you can just pick off the numbers. If this was an open circle, then this would be just less than. If this was an open circle, this would be just less than. Sometimes one will be open, one will be closed. So the closed tells you to make it or equal. The open tells you to make it just less than or greater than. Then the last piece over here, it's greater than because it's going to the right. It goes from here to the right. It lines up again with x equals 2. And since it's an open circle, it's going to be greater than and not greater than or equal to. So it's just greater than 2. All right? Those are my if statements. Now the thing when you do this, you're usually not going to have to write the domain and range. But if you do, this is your domain. Okay? In this case, it even picks up. It's actually, the domain is all real numbers. Because even though there's a little wall here, it picks right up here. This 1 is covered on both. This 2 is covered in both. So there's no x that's never on the graph in this case because there's no gap between 1 and 1 or 2 and 2. The next thing that we have to do is write the equation for each of these points, or pieces, sorry, each of these pieces. This one's super easy, to be honest with you, because it crosses the y-axis, which means I know the y-intercept. The y-intercept is 1, 2, 3. So I know it's plus 3 already, right there at that point. I know this part of the equation is going to say something plus 3 because we think of slope-intercept form, mx plus b. The b is the y-intercept, so I've got that. Now I just need to find the slope of this thing. Well, I've got a point here and a point here, and you guys showed me on the last test that you can find the slope from a graph. So I go up 2, 1, 2, right 1, that's 2 over 1, so my slope is 2. So that piece is 2x plus 3. This equation, the equation for this line is y equals 2x plus 3. Okay? Now this piece is a little trickier because it doesn't cross the y-axis, but the equation itself will still be in the same form. So if I knew what the y-intercept was, if it continued on and on, I could find the equation for this piece. So that's what we're going to do. So if you notice here, if I just back it up one, because if to get from here to here, I go left one, up one. If I go left one, up one again, it'll line right up. Well, that value is 2, which tells me this piece has a y-intercept of 2, even though 2's not even on it. But these conditions are what sort of cut it off, okay? And if we were to plug, and after we do this, I'll talk about that. But so let's talk about the slope. So you go down 1, right 1, down 1, right 1. So that's -1 over 1. So my slope is -1. So even though that's my equation, if I were to plug the value in, 1 here gives me 1. Well, there's the point, 1, 1. If I plug 2 in, I get 2, 0, 2, 0. There's my points. So I can just plug them in and plot it. So that just verifies that even though this is a linear equation, y equals -x plus 2, this piece, because of the conditions, basically chops it off. And then the last one is a horizontal line. And horizontal lines, will always be in the form y equals. Just like I showed you on the other one with the dotted line, the vertical lines are always in the form x equals. So in this case, this y value, all the y values on this line are the same, and they happen to be 3. So in this case, this piece of the line is just y equals 3. So what we put here is just a 3. So that's what we're doing in 2.6 piecewise functions. We're going to write equations from a graph using a lot of slope-intercept stuff, but you've got to pay attention to the boundaries. And so that's where the idea with domains and walls and that kind of thing still comes into play here. And then also we have the other one where we're given the function and you're going to have to do the graphing. So there's a lot going on here. You won't have that many problems to do for homework, but they're intense. There's a lot to do. So just take it one piece at a time, literally, and you'll get it.